Okay, so we're going to start part 3 of the material extrusion lecture, looking at some of the different types of 3D printers using the material extrusion process, and we'll start with the Stratasys FDM process. We've already seen this figure at the beginning of the lecture presentation, but we'll look at it again here. There are, in the Stratasys FDM, there are 2 filament spools. One is for the build material, shown here in dark blue, and the other is for the support material, shown here in light blue. The filaments are fed into the extrusion head here, okay, and we have 2 nozzles on this Stratasys machine. Okay, one nozzle is going to be exclusively for the build material, and the other nozzle is exclusively for the support material. Okay, and this is going to help in keeping the nozzles clean, and also in, of course, the speed of the printing process, and not having to constantly fill or remove material and then add a new material, obviously. To speed up the printing process. Okay. Also, I would like to point out also how the build platform and the axial directions work for the build process. In the Stratasys machines, the Z direction is going to control the build platform. Okay, so Z is going to be up and down in the build platform. And the X and Y is going to be controlled, or the XY direction of the print is going to be controlled by moving the head. So here we have the head is moving. In some of the other examples, we'll see examples where the table actually moves. So there's a lot of variation here in how you're controlling the axial motion to actually print the part. But in the Stratasys, Z is going to be the build platform moving up and down, and the head moves in the XY directions. All right, now here's a short video of the process again. And again, I'm not going to necessarily go through the whole video. I'll go through different sections so that we can just see the interesting parts that we want to focus on.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform.
Now, in
thin thread-like spools of thermoplastic.
In this example, they're using, this is a sample like a Stratasys machine, okay? And you can see the 2 build heads, or excuse me, the extruder nozzles, and the 2 build materials, or excuse me, the 2 filaments, the build material and the support material.
And support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material.
Okay, I think we can move on from that. And now typical FDM characteristics, again, these are typical of the Stratasys machines. The accuracy is at least plus or minus 100 microns. Resolution, maximum resolution is 600 dpi or dots per inch. Okay, layer thickness is 900 or 1600 dots per inch, depending on the settings, right? So this is a common setting in all of the Material Extrusion 3D printers, is what layer thickness do you want to use? And in the Stratasys example here, the characteristics, you either have a 900 or 1600 dots per inch layer thickness. Build volume is quite large in both of the 3D printers that we have in our lab. There, it's basically 8 inches by 8 inches by about 12 inches, so it's quite large. And that's indicative of material extrusion. Material extrusion can handle these large shapes, these large volumes quite easily. And the material, as we already discussed, is thermoplastics. Here's some examples of different material. These are all Stratasys examples, and you know, it's really interesting to point out the wide range of finishes, colors, whether it's translucent or whether it's solid. And so that's one of the attractive natures of the material extrusion process. Now, there's a lot of other FDM printer styles, or more precisely, fused filament fabrication, material extrusion, 3D printer styles. Okay, so what a style is basically how the print is going to occur, manipulating the axial directions, right? The X, Y, and Z. All right, and so we have SCARA, Cartesian, which is like the Stratasys, and the most common one, Cartesian. SCARA, Cartesian, Delta, Polar, 5-axis, and then there's some weird ones out there. So we'll have a look at some of these. The Cartesian style is the most common, right? It's the easiest to program, and so I think that's why it's the most common one. It also is very predictable in how it's going to print, and how, remember, you need to control things like print head inertia and all those things. So in this case, the XY plane is parallel to the print bed. The Z axis is in the build direction. In the example here, we have the head, the printer head is going to move up and down in the Z direction, and the table is going to move in the XY plane. Remember that in the Stratasys example that I showed you, the table moved up and down and the print head moved in the XY. So this is kind of the opposite of that. But as you probably can guess, both options are available to us. Advantage of this process is it's very common, it's mechanically simple, it's easy to program and calibrate, and it's easy to control. Disadvantages are you have to deal with the printer head inertia, right? And so that means you have to control the acceleration and deceleration of the print head, as well as the flow rate of the material. The other disadvantage is it's relatively slow. Now, another process that actually is fairly common, maybe common is too strong of a term, but you don't have to look too hard to find examples of a delta process. Now, delta, the print head is going to be controlled by these three kind of actuators that are going to move up and down on these rods, okay? And they're also going to control the position of the print head, which is here, by reeling in or letting out the cables that are going to support it. So the print head moves vertically in the Z axis, right? That's what all these are. Here there's a circular bed. I don't know whether that's a requirement, but in this example, it is a circular bed. The advantage is that this is a very quick process, right? Basically, you have more control of the inertia of the print head, all right? And that's why this is a quick process. Also, the build height is only constrained by the length of these rods. So you can build extremely tall parts just by extending these rods. The disadvantages are that this is very mechanically complex. I'll show you a video in a second where this is working. And you can guess that this is going to be very tough to build and then also to program. It's also difficult to calibrate. And then these rods right here, the flexibility of them is going to greatly impact the accuracy of the part. All right, so let's look at a quick video of this. Again, we won't look at the whole video. We'll just kind of look at the snippets that we need to. So this is called the Delta Wasp 2040. And you can see the rods are quite tall in this. So here we have bed leveling, so it's making sure that it knows where the bed is, the build platform. This is a single filament extruder. It's kind of showing off the span length that it has for that, but we're just looking at how it's being built, and you can see how that moves. All right. Now, if we look at, here's another example of one. This is a high-speed 3D printer. I'll keep the sound on so you can hear, but it's just going to be the 3D printer. Now, you'll notice right here, let me pause it for a second. This is a fan, okay? And the fan is blowing on this basically to help it cool, right? So the material that they're printing, this, you know, I don't know whether this is ABS or not. Probably not, because they probably don't want to cool it that fast or that quick with ABS. All right, so this is probably something along the lines of PLA, a very common material. But you can see this is very fast. Okay. Now, a third type of 3D printer is the SCARA type of printer. Now, SCARA stands for Selective Compliance Articulated Robot Arm, and it is a common robot arm, or the geometry configuration for a robot, okay? Especially a very high-speed robot, right? So a SCARA robot has limited range of motion, but it can move very fast. The advantages here, it's very precise, right? Because we're controlling the printer mass, especially in configurations where we have this double SCARA arm, and very large build volumes. Disadvantages is it's experimental. So I don't know whether you'd ever see one of these that you could purchase. Let's look at a video to see how these work. Right? And we don't need to listen to that. And you can see, so the arm is just this articulated arm. We have a joint right here, and that's how it's controlling the print head. All right, it's actually very simple. You know, the mechanism for this is very simple. Let's look at another example. Now, this one is, it has a double SCARA arm configuration. So you have two of these arms that are going to be holding on to the print head. So let's see how this looks. Obviously, this is sped up. But you can see now we're able to control the inertia of the print head very, very closely. So again, these are kind of experimental. So I don't know whether you'd see this. You probably would never see this in that you can purchase at your Best Buy. Now we're getting into some of the stranger ones. The Polar printer. Uses a polar coordinate system. The bed spins and moves laterally, right? So it spins and then it moves. In this figure, the bed is going to move left and right, okay? And the print head is going to move up and down, right? Advantages are you have two stepper motors, right? So minimal use of the motors, and you have a large build volume. The disadvantages are it's very complex to program. it has compounded print errors, right? And it's difficult to heat the build plate because the build plate moves, right? And so you end up moving a lot of equipment, which again is going to affect the inertia. All right, so let's see an example of a Polar printer. And there you go. You can see the table moving in and out towards and away from the camera. The table is spinning. And it's a little bit difficult to tell, but you can tell that the print head is moving vertically upward. All right. Then we have these are actually common for the large area additive manufacturing, such as the BAM. Remember, that's the big area additive manufacturing machines. And it just makes sense because really to upscale the whole mechanism for 3D printing, it makes sense to use an industrial robot. Okay, because a robot is a readily available way to control the positional, the position and the accuracy of a end of arm tooling, essentially. So that's what we're doing here. In this case, the 5-axis, it uses a polar coordinate system. The print bed spins. The print head moves vertically. Advantages, 2-stepper motors, large build volume. We'll see 2 examples of this. So this is where we're controlling. You can see the stepper motors right here. So this is where we're controlling just the print head, right? So we can rotate it around this axis, and we can rotate it around a vertical axis. Let's look at an example of this. Now I'll leave that on. That sound is the servos speeding up and slowing down, controlling that head. And the advantages here is that we can print over curved shapes, right? So notice that in a traditional 3D printer, material extrusion 3D printer, we can't print. We're constrained to print on a flat build platform. So here we can more control the contour of the 3D print. All right. Let's look at another example. Now this one is attached to a Universal Robotics cobot, and you can see the print head mechanism here. And again, we're printing on a, as it says, a complex and bent surface. Now it takes a while for this to get going, but you'll see it. There we go. And so now it's tracing that shape and it's printing around the curvilinear surface. Again, experimental, so you're not going to see this at your Best Buy or on Amazon. And then we have some hybrid. So this is a hybrid combination of Polar and SCARA. Again, as the sign says right here, as the title says, it's not practical for use. It's experimental. This one's kind of dizzying. So we'll get this going right here. All right, and you can see that printing it. All right, and again, if you're wondering why somebody would want to do this, that's a good question. Now here, this is an interesting one. This is called a Dogleg Delta. So it's a Delta kind of 3D printer, but it has elements of a SCARA robot in it, right? Or similar to a SCARA robot. So let's see how this works. All right, and so it almost looks like, it reminds me of, maybe 3 people stirring a pot, stirring a soup or something like that. Again, not very practical, but experimental. All right, so we'll finish up with just the last slide here, talking about future directions in material extrusion. Material extrusion is really one of the most explosive areas for 3D printing. There's a lot going on here because The technology is not very complicated. It's readily available. There's a lot going on with materials. One of the biggest things on the market right now, especially in the industrial market, is metal material extrusion. And this is an example of that. So it's using the same principles of the fused filament fabrication of material extrusion process, but in this manner, what they've done is they've taken the filament and they've filled the core of the filament with metal, right? And so when you print, right, you're basically printing a plastic, right? The filament is plastic surrounding a metal powders or metal fibers that are then going to, when you melt the plastic away, which you have to do in a secondary process. So you print the part looks like, just a normal plastic part, but, it has metal inside of it. And then you take it to an oven type system, and you put the part in that oven, and basically you melt away the plastic and you sinter the material, the metal, which is, you basically kind of bond the metal together. And so you end up with a part that is metal, right? And so this is very exciting because you can actually print metal much stronger. Some of the same companies that are doing the metal printing have figured out how to put strands of fiberglass and Kevlar and different materials in each print layer. So you can see those here. These fiberglass and Kevlar strands greatly increase the strength of each layer and the subsequent part. The fiberglass can be deposited in all different configurations, and you can selectively apply it in layers or avoid it in certain layers. So it's a great machine. We have one of these machines in the Moraine Valley 3D printing studio, the Mark Forged Onyx machine, and it's a lot of fun to print and play around with the configurations for that. And finally, they are 3D printing homes because, if you just look in this small figure, you can see that the material extrusion process, especially the Cartesian print style, just lends itself very well to large scale printing like this, like you would find in a home. So the filament, quote unquote, the filament that you're going to be printing is going to be cement, right? And the cement has the correct consistency, so it's not going to, just flow very easily. It's kind of like, a more solid, if I can use that term, cement that's pumped in. You can see the crane here that's pumping the filament down into the print head. And the print head is going to be traveling on this gantry system, both laterally left and right, and the gantry is going to be moving on these rails down here. So it's basically a gantry system, which is very common in industry and in factories. And a boom that's going to be pumping this cement mixture into the print head. And these homes are being built right now. They're being built in, I know that they're building them in China and in parts of Africa. So look forward to these being printed in your neighborhood very shortly. All right, so that finishes up our material extrusion lecture. This is part 3. So I will see you in the next lecture.